All right, I started drawing some of these out for you already. Here we go, part three. R is at, the scale on this is really bizarre. R is negative 1, 1, which is right there. If you look carefully at these scales, that's where that goes. And which other one I forget? V, negative 1, negative 3, which is right there. So this is a trapezoid. Looks like a trapezoid. All right, so R to S, that looks parallel to S. Wait a minute, that wasn't S. I gotta change one of my S points. I got too many S's. I don't have enough V's. All right, I think I know what I need to do. All right. Yeah. This is an S. This is V. Sorry about that. V is at negative 1, negative 3. Okay, great. So yeah, these scales are weird. This scale, each one of these is a half. This scale, each one of these is 1. So just be careful about that. Graph trapezoid, blah, and its image under the line of reflection, y equals negative 3. Okay, so let's draw the line y equals negative 3 first of all. Y equals negative 3, that's the line where all the y coordinates, which is all the heights, they're all the same, they're all at negative 3. So that line is actually a horizontal line. I'm gonna change color maybe. It's a horizontal line right here. All right, so that's the y equals 3 line. I kind of don't like that it's being the same color. Let's change the color of that. Let's change that to blue. How about, will this make it blue? Y equals negative 3 looks like this. Okay, so that's the horizontal line, y equals negative 3. Okay, sorry, it's taking so long. So this is our mirror line. This is the, if you want to write this in correct transformation notation, it's kind of like this. I'm going to reflect this guy over that. Oh, let's make a new color too, something you can kind of see. Point V isn't going to go anywhere. Point V is going to equal point V prime because it's right on the mirror, so it doesn't go anywhere. Point T goes, well, it's 2 above the mirror, so it's going to go, perpendicular. Here we go 2, go 2 more down that way. That's T prime. S was 4 above, so it's got to be 4 below. That's good. This segment from T to S should be 2 segments long. Because it was 2 segments long before, it should be 2 segments long after. V is there. All I got left is R. And R was up here, 4 above, so it's got to go 4 below. Am I counting tick marks right? I think I actually am. So that's R prime. And I just connect the dots. Yeah, I think this will turn out to be the right color. Yeah, good. Connect T prime to V prime, connect V prime to R prime, and that's my new trapezoid. Okay. All right, find point Q if the reflection over line, oh, that's the x-axis. Oh, I've been using x-axis. I believe this means the same thing as x-axis. If I reflect 5, negative 2 over the x-axis, it turns into P. And then when I reflect that point over the y-axis, it goes to Q. I could do this with pictures. Actually, you could do it without. We know what happens to points when you reflect them over the x-axis. You reflect points over the x-axis, the x-coordinate stays the same. That's how you remember that. When you reflect over the x-axis, x stays the same. When you reflect over the y-axis, y stays the same. The other coordinate changes signs. So here we are. So I could even say right here, I know that the coordinates of P, P is at, well, this original point was 5, negative 2. When I reflect that over the x-axis, the x stays the same. The y changes signs. So then I'm going to take that and reflect it over the y-axis to become Q. And when I reflect over the y-axis, the y-coordinate stays the same, but the x-coordinate changes sign. I might as well draw this. This won't take that long to just draw out. Just see what's going on here. I don't have a name for this. It's okay. All right, so here's the x-axis, of course. You forgot which was which. It was the y-axis. This original point 5, negative 2 was here. Original point. First thing we do is reflect that over the x-axis. Well, that's going to be something like this. Do you believe me now? This is P. It's a reflection of that point over x, and that's at 5, 2. It's just like, well, I had to go towards the mirror and then keep going. Now reflect this point over the y-axis. So it's going to go way over here somewhere. Looks like it's going to have to go that far on that side. And yeah, that's the point Q, and that's at negative 5, 2. That's kind of what that looks like to get this final answer. All right, last one. Joy. Oh, Joy. She's waiting at the cafe for a friend to bring her a ticket to an event at the sports arena. So she's here. She's starting out here. Oh, let's just call this J. And then she is going to meet someone in a car. Sounds like a shady operation. She's going to meet someone in a car somewhere along this road. and then she's going to walk from that car. Like maybe it's here, maybe it's here. The question is, where should she go along the road to meet that person at the car, and then walk to this entrance, assuming that it's okay to walk on all this lovely grass. I guess there's no sidewalks where she's at. What kind of sports arena is she going to? Anyway, so she goes towards the road and towards the entrance. The question is, can we find the point on the road that's going to be the best place for her to do this so that it's not like totally out of her way? Certainly if she walks way down here to go to the road and then way back here to go to the entrance, that's like way too far. If she walks straight down to the road, that might seem convenient. And then over to the entrance, I don't know, that might be the quickest. Or like straight over here right by the entrance, kind of perpendicular here and that way. Turns out none of those are the right answer. A common answer people like to use for this is I'm going to erase this in a second because it's wrong, is they go, okay, let's go perpendicular to the entrance, find out that point is. Let's go perpendicular to where she's at now. Let's find the midpoint of that whole thing, and let's try that. No, that's not it either. We're going to use the power of reflections to figure this out. It turns out, this is kind of unrelated to everything we've done so far, but in terms of why it solves this problem, it's not unrelated in that the answer is about reflections. Let me just stop talking and do it. The reflection line here is, believe it or not, we're going to use this road as the line of reflection. We are going to reflect the entrance over that road. So if I reflect the entrance over that road, it's going to be, again, I would do this technically with a ruler. Measure with a ruler so you're going perpendicular and keep going just as far on the other side. It's going to be somewhere down here. So I'm going to call this point E. This is point J. I'm going to call this point E prime. And that came from the reflection. Oh, I need a name for this line. Let's call this M for mirror. I know it's street for S, but my S's look like 5, so we're just do that. Reflection over line M of point E. So there's this cool property of reflections. If you were to now, so for her to find this point on the road, what she needs to do is aim at this imaginary reflection point E over here. Your mind blown yet? And of course, she's not going to walk over there. That would be, well, first of all, probably illegal and dangerous to cross the road and walk off the face of the earth down here. But no, she's going to aim at this point over here, because what ends up happening is, by doing so, she's going to walk towards that point. Of course, she's going to stop when she gets to the road. But in doing that, in aiming for this right here, she will have located the answer to this question. She will have found that place where she should bounce off the road and minimize her total walking distance. Why is that the minimum? Kind of hard to explain. Why is this red path up here above the road or to the north of the road equal to the path of the entire red line from J to E prime? That's easy to explain. Notice this little thing would have to be the same distance as that little thing because of what we know about perpendicular bisectors and how reflections make distances the same. The reflection of this point is the same point. The reflection of this point's over here. So the reflections of before and after kind of segment here would have to equal the before and after segment here. All right, and then add this to both. You get the L-shaped path over here and the full path over here. They're the same. Why is that minimized? Well, we can talk about that in class. Any other path to go to the road and then back here would be the same as the point from there to here and there to here, and that is longer, my friends, than the straight line from J to E prime. It basically all comes down to the fact that the shortest distance between any 2 points is a straight line, and we're modeling that here with J E prime. And I can prove that J E prime is the same distance as J to here to E. And anything else will have to be from J to the line to there, and it's going to have to be longer because it would represent a triangle if I was headed towards E prime. So anyway, yeah, that's kind of cool. There's other properties about that, like that kind of picture. We're going to do some problems about miniature golf and billiard tables and that kind of thing. If you were here at J and you bounced a laser off a mirror right here, it would, if you're aiming at the reflection, this imaginary reflection off this mirror line, if you aimed your laser pointer at this point, it would bounce off the mirror and hit this entrance perfectly. Or if you bounced a billiard ball off the edge of the table or a basketball off the backboard, that kind of stuff. Or a miniature golf off the wall, that's the same thing. These angles turn out to be the same. This is the property of physics we're trying to model here. So all those billiard and pool examples or lasers and mirrors, they have to do with this too. The trick is take the target that you're trying to hit, reflect it over the line that you know you have to bounce off of. And here, by bounce, I mean go to the road and then turn around. So that was a bounce in my mind. Reflect the target off or over the bounce line to get an imaginary target, and then aim straight at that imaginary target. And this is always going to happen. And it's going to minimize the distance, and it's going to work for lasers and miniature golf. Okay, I've wasted enough of your time. Enjoy. See you in class. I know you can't wait.